Maybe before we talk about some of your other research, for those listening that aren't familiar with complex system science, maybe you can explain some of the characteristics that allow this kind of interdisciplinary, cross-disciplinary work. What are some of the fundamental tenets of complexity that allow this kind of broad sort of work?
Okay, maybe what I'm going to say doesn't fit very much to epidemiology, at least in a standard way. But it is the question of how to connect the little rules with the phenomena of the macroscopic phenomena of the whole system. That's our main, the main question that I always try to tackle when I work in these things, mainly, as I told you, with the students. And it is how little rules change or define the function of the whole system. Mm-hmm. So we use statistical mechanics or statistical physics. Mm-hmm. But the first part usually is, as I told you before, how to represent the small part, the microscopic part of the system. And afterwards, how to connect that with the macroscopic phenomenon. And so that's a very important part of thinking in complexity, or in my way of getting into complexity. In the case of epidemiology, part of it was stochastic, how we call it, but part of it was deterministic. It means you know math, you can solve some problems, and that's what we did, solving analytical problems, mathematical problems in partly an analytical way, partly using numerical methods, and obtaining the solutions and interpreting the solutions. However, when we got at the end of the road of the epidemic, we were very happy that we made it to get it to use methods which are more close to this perspective of complexity.